It's funny when you stop and think about it. So much of our world is constantly spinning. Seriously, from a little kid's top to the wheels on your car, all the way up to the Earth itself, rotation is just everywhere. And it all follows these beautiful, kind of hidden rules. Today, we're going to unlock one of its coolest secrets. And it all starts with a scene you've probably seen 1,000 times, an ice skater. They start their spin, arms out, all graceful, turning at this nice, steady speed. But then, they do something that looks like straight-up magic. They pull their arms in tight, and bam! They suddenly speed up, turning into a total blur. How do they do that? There's no engine, nobody's pushing them, so what's going on? So yeah, that is the big question we're going to solve in this explainer. And it's a question that takes us right into the heart of rotational physics, which is basically where the normal rules of motion get a really fascinating twist. Okay, so to figure out the skater, we've first got to get a handle on the basic rules of spinning. And honestly, the best way to wrap your head around it is to realize that for pretty much every rule about moving in a straight line, there's a matching rule for spinning. This table here lays out the whole analogy perfectly. What we call a force in a straight line becomes torque when you're spinning something. Think of using a wrench. And mass, how much something resists being pushed, becomes this thing called moment of inertia, which is how much it resists being spun. And that idea right there, that's the key to this whole thing. Right, so this is super important. An object's resistance to spinning isn't just about how heavy it is. It's about something way more interesting, its shape, and really how all of its mass is laid out. This is where we find the real secret. So let me introduce you to the moment of inertia. Honestly, you can just think of it as an object's rotational laziness. It's a measure of how hard you have to work to get it spinning or to stop it. And the key part of the definition is this. It's not just about the mass, but about how far that mass is from the center of the spin. This quote from a physics textbook just nails it. Imagine you have a solid disk and a hollow ring, and they both weigh exactly the same. The ring is going to be way harder to get spinning. Why? Because all of its weight, all of its mass, is way out on the edge, far from the center. It has a higher moment of inertia, way more of that rotational laziness. And this visual just makes it so obvious, right? On the left, you pack all the mass in tight to the center, and you get a low moment of inertia. It's easy to spin. But on the right, you take that exact same amount of mass and just spread it out, and its moment of inertia skyrockets. It gets way, way lazier and harder to turn. Okay, we have all the pieces of the puzzle. We get what moment of inertia is, so now let's bring it all back to our skater and finally solve this mystery, using one of the most powerful laws in all of physics. And here is that law, the conservation of angular momentum. What that means, in plain English, is that the total amount of spin an object has can't change, unless some outside twisting force, a torque, messes with it. And that amount of spin, the angular momentum, is just its moment of inertia, that rotational laziness, times its spin speed. So let's look at our skater one more time, arms stretched out wide. By doing this, she's spread her mass as far as possible from the center of her spin. This gives her a huge moment of inertia, a lot of that rotational laziness. And because her total amount of spin has to stay the same, her spin speed has to be pretty slow. And here it is, the magic moment. She pulls her arms in. Instantly, all that mass comes rushing in closer to the center, and her moment of inertia drops like a rock. But that law of conservation is absolute. Her total amount of spin can't change. So since her rotational laziness just went down, her spin speed must go up to balance it all out. That's it. That's why she spins faster. It's not magic at all. It's physics. And this is not just for skaters. Watch any professional diver. They leap off the board, and to get enough spin for all those flips, they pull into a super tight tuck. That makes their moment of inertia tiny, which makes their spin speed huge. Then, right before they hit the water, they open back up to slow the spin for a perfect, clean entry. It's the exact same principle at work. But what's really mind-blowing is that this rule isn't just for athletes here on Earth. This whole idea, this conservation of angular momentum, it's basically woven into the fabric of the entire universe. Just think about that for a second. The exact same law of physics that lets a person control their spin on a frozen pond. It's also what directs the dance of the planets. As a planet swings through its orbit and gets closer to its sun, its moment of inertia in that orbit actually goes down. And to keep its angular momentum constant, its speed has to increase. It literally speeds up. And then it slows back down as it moves away again. From a skater to an entire solar system, the rule is the same. So, the next time you see something spinning, I don't care if it's a toy, a bicycle wheel, or you're looking at a picture of a giant, swirling galaxy, ask yourself, where's the mass and how is it moving? Because now you know one of the deep secrets that keeps our universe spinning. So what else out there is playing by these same hidden rules?